Hello and welcome everyone to today's Mahr Surf webinar, Start to Finish, Surface Finish Measurement Overview and Best Practices. I'm George Schuetz, your presenter. I'm Director of Precision Gages at Mahr in Providence, Rhode Island. Here's my email address and phone number, and feel free to contact me anytime you wish. If you have any questions during the presentation, use the chat feature, and I will respond to your questions after the webinar by email. So as an introduction, surface finish inspection has become a normal part of the part measurement process. Mahr has a full line of surface finish products. They range from very basic, easy-to-use portable surface gauges to powerful roughness profile and waviness systems. And today, we're going to talk about the importance of surface finish. We'll talk about the basics, some of the parameters and things to watch out for when you're trying to measure surface finish. And then we'll give you a quick overview of the Mahr Surf portable surface finish line of roughness gauges. So let's begin. As dimensional tolerances have tightened, form and surface finish errors have become more significant. So you can see this chart on the right here that represents tolerances from the 1940s all the way through today, basically, and tolerances have shrunk a lot over that time. Mostly because of aerospace applications, automotive, medical, electronics, and even precision machining. Tolerances have gotten tighter and tighter, but the form tolerances has also gotten tighter. But still, that percentage of surface finish and form errors compared to part tolerances is now, it might be 25 or maybe even 50% of the part tolerance. So it's important to consider surface finish and how they can affect the part performance, appearance, etc. So why is surface finish something that's important to control? So here's 3 or 4 examples of where surface finish is something that needs to be controlled. And the first one is appearance. Surface finish really affects reflectivity and consistency of the surface. And you can see here a couple of pictures of 2 parts with different surface finishes. One's kind of shiny, one's more matted, and the way the quality of parts appear to people can be very, very important. And so it's important to think about controlling surface finish to make sure that part appearance is consistent. How surfaces function is another important reason to control surface finish. One is the adherence of coating. When you think about painting something or applying a finish to it, if that surface is too smooth, maybe the paint's not going to be able to stick to it. Or if the surface is too rough, the paint may not cover it properly, and you'll see some ridges or unevenness in the painted surface. So coating adherence is an important reason for checking surface finish. Also, slide interaction is an important reason, how things move together. So, when you think about 2 surfaces sliding against each other, you would think that you would want a relatively smooth surface. But no, you may want to be able to control the surface so that you have a nice a bearing area, but there are some grooves in that surface to allow us to hold a little bit of oil. So you can see in that plateaued picture at the bottom here, I'm sorry about this, that the surfaces peaks have been cut off. There are some valleys in there, and we can hold oil in those values to make that surface function better. So surface function is another reason for controlling surface finish. And you may want to monitor the surface finish to maximize the process. We'll see how machine parameters, feeds, and speeds affect and create the surface finish. Well, you might want to be able to monitor the surface finish to maximize the processes, but still get the same quality that you want for your part. And you can also analyze the surface for any process problems. Maybe the machine tool is putting surface conditions into the part because a bearing is going out or something like that. So that's another way of understanding what's happening to the manufacturing process. So these are all important reasons to control surface finish. So where does the surface finish come from? We talk about the machining process, and here's a typical lathe, and the parts of that lathe are going to really put a fingerprint of that manufacturing process onto the part. So those parts of the process are, the cutting tool itself, the ways and the lathe bed, for example, they have some straightness errors in them. You might be getting some vibration from the motor or the gearbox. And all those really become a fingerprint on the part. So here's the example of the tool marks, the vibrations, which is causing waviness, long-term straightness errors or form errors that can be imprinted on the part. So all those things give us a total profile, and they can be separated out by different types of filters, but roughness is the one that most importantly affects what we're trying to measure in a part, and that's what we're going to talk about mostly today. So how do you measure surface roughness? Well, basically they started with scratch pads in the past, where there were machined patches with different feeds and speeds on them to give different surface roughnesses. And before they were qualified, it was a visual check, and then using your fingernail, you can kind of get a sense for how rough that surface was. And a part would be compared to that roughness patch using your fingernail as a probe, basically, and that's how items were qualified at one time. But now there's some more sophisticated methods for doing that, well documented with lots of standards, where there's a mechanical contact that's dragged over the part to get the surface roughness. And now there's even some very powerful and important optical imaging systems, whether it be 2D or 3D imaging, that can give you a surface area measurement for roughness or for profile, and which can correlate very good to the mechanical contact methods. So, primarily today's way of doing surface roughness is with mechanical contact, but optical systems are becoming more available. Most of the equipment sold today is the contact method, and there are basically two different methods for doing that. Mahr provides both types of surface evaluation instruments, whether it be portable. Most of the portable ones use this skidded method. And with the skidded method, a probe is dragged over the surface. There's a skid, that's why it's called skidded, and in the middle of that skid usually is a probe with a very fine contact tip on it, or stylus, that records the surface profile or surface roughness. So as the skid is dragged over the part, the skid is going to follow the long-term surface conditions, the waviness or the profile, and just pick up the roughness parameters. So skidded instruments measure only roughness. Waviness is filtered out by the skid following the surface, and most, like I said, most portable instruments are of the skidded type. Now we also have a skidless type of measurement. This is where you have a precision datum guide inside the drive system, and the probe itself, the very fine stylus, is moved over the parts. So now, compared against that straight datum, this skidless system can measure roughness, waviness, and profile. So these systems are a little bit more expensive because they have to have the straight datum in there, but they can give you more information in terms of roughness, waviness, and profile. So Mahr makes both these types of systems, and we also make the optical systems, as I mentioned previously. Now, there's lots of ways to measure roughness, and there's nearly 100 different parameters for surface finish evaluation. And they can be used for some very basic information about the surface, but by using different parameters, we can talk about the stability of the manufacturing process, the functional characteristics of the surface, and we can also talk about the analytical capabilities of instruments to help understand what that surface can do for us. But the most common parameter in use today is R sub A, or RA. Since the roughness profile contains peaks and valleys of different heights, an averaging method is used to quantify the surface. So R sub A stands for roughness average. Other common ones are RZ or R max, and we'll talk about those in a minute. But what we can see here is that we're taking a series of small little segments over a long length, and we're going to look at the average of the peaks and valleys within those segments to give us R sub A. So R sub A is the go-to method for most analysis. It's often the most common one specified here domestically in the U.S. It gives a pretty good general indication of what the surface is. It's easy to understand, it's visible, it's better than the old scratch standards that are out there. And it's easy to quantify because knowing the RA equals 75 microinches, for example, you can tell by a larger or a smaller number whether the roughness average is larger or smaller. So it's a good way just with a value to quantify the surface. And it's easy to understand. Like I say, RA is the most commonly used parameter in the U.S. There is some confusion because at one time people would refer to RA, which came from RMS, or root mean squared method for analyzing the roughness, but they're really not the same. RA is the arithmetic average of the absolute values of the roughness profile coordinates. So RA equals arithmetic average or centerline average. RA does not equal RMS. RQ is a parameter which equals RMS. But again, R sub A, or roughness average, is the most common parameter used today. And there's a ISO standard, an SME standard, that defines how the RA is calculated. Now the issue is that sometimes surface finish is different due to bearing contact. So, here we have a RA that's specified, it's available for monitoring the process, but these two surfaces can give us the same RA value. So it's important to understand that, and maybe sometimes other parameters could be required to monitor the surface function. So here's another one where RA is giving us the same parameter, but R max might be a better method for analyzing and helping evaluate the process. So you can see, here's a surface that has a roughness form to it, basically, and here's the same one that has a couple of very high peaks and valleys to it. But if you, over a period of time, those peaks and valleys might average out, thus giving us the same result. So our max might be a way of analyzing this surface because it's going to pick up that very high peak in the surface and give us some more information. So, different parameters will help to analyze our surface. So for the rest of the world, R sub Z is the most commonly specified parameter. It's an average of the vertical distance between the highest peak and the lowest valley in 5 sampling lengths. So it's a little bit different. It's much more sensitive than RA to changes in surface finish because heights are examined and looked at rather than the averages. So there's really no important thing to remember is, people try to convert R sub Z to RA, and there really is no formal conversion between those parameters. You have to measure that surface with the R sub Z or the R sub A parameter. There are lots of best guess estimates out there where RZ could be 4 to 7 times the RA value, but what's 4 to 7 times? And that's basically a useless conversion. So if you want to measure R sub Z, you measure R sub Z. If you want to measure R sub A, you should measure R sub A with the equipment set to that parameter. Now, here's that same slide again where we talked about R sub A having the same value for both of these areas. And these are, two bearing type of surfaces. And you can imagine that the bearing surface on the left one is probably not as good as the bearing surface on the right one. And just to know that there are ways that with using parameters that you can start analyzing these bearing surfaces if you need to. And that's through a material ratio example. So, you can see that if you had these spiked or peaked surfaces and that more rounded one, the bearing area on the peak surface is very small compared to the surface here. And by using a material ratio example, you can start cutting down on the surface, or say I want to take 20% off that surface, it can calculate for you how much bearing area is available, and you can do the same thing for the this surface here with the more rounded area. So by using a calculation which is available in many of the portable surface finish gauges, you can start analyzing and predicting, for example, how much contact ratio is at a given depth. So, you can see with a sine wave that at a depth of 50%, you can calculate what the contact ratio is going to be. Now, I don't want to get into too much details, but I just wanted to show you that, here's 3 areas of surface roughness, R sub A, R sub Z, and material ratio, that you can start getting information about your surface from the portable surface gauges available today. just like anything else, just like any other measuring process, surface finish measurements is a process. And many times before we've talked about the measuring process using the acronym SWIPE, the standard, the workpiece, the instrument, the people, and the environment. And each one or each part of this measuring process or element can influence the results. So the same thing, whether we're talking about a dimensional measurement or a surface finish measurement, this can be influenced by each one of these parts. And sources of surface finish from the instrument itself can be discussed and should be considered while making the measurement. So here are some of the sources of errors. So non-adherence to the measurement conditions. We talked about measuring segments of the surface and how long the surface was and the type of tracing systems. So anytime you do a surface finish, you should verify that those parameters are all set up. We have the right parameter, we have the right length, and we have the right tracing system. Otherwise, there's a chance that a measurement I make here or a measurement I make in another factory or another location could come out different, even though the surface finish really might be the same. There's also different grades of surface finish equipment out there. Systems can run between 5 and 25% inherent errors. That's something to consider. There are different types of probes out there having different styli radiuses of 2, 5, or 10 microns. It's important that if you're comparing results between equipment, that you're using the same styli radius. Systems have different force, which is to be considered, or the tracing speed, or the sampling rate. Any one of these can affect the results that are obtained. In terms of the setup itself, vibration in the environment is going to cause readings or an influence on the results. If a part is moved during the process, that's going to cause an inconsistency within the results. Driving or guiding difficulty. If there's something going wrong with the drive, if it's getting stuck during its process or some grime might have got in there, that can affect the results. The wrong tracing system may cause some distortions in our process. We want to make sure that the tracing system is aligned as close to parallel to the surface as possible, as the pictures indicate here. We don't want a dirty surface because that can influence the readings, and we want to make sure that we don't have a worn or damaged probe. All of these are sources of errors in our surface finish measurement process. So again, not understanding the parameters, selecting the wrong gauge, selecting the wrong cutoff, sometimes relying too much on default considerations, not choosing the right processing filters, using the appropriate tip, or even ignoring the measuring force can affect our readings. So you can see how a very soft surface can be damaged by the tip and influence our readings. All of these things are things to consider. And you can check the performance of surface finish gauges, and there are tools out there to do that. So these standards have been developed to help define the specification, the use, the results, and testing of the surface finish gauges. Since the surface finish consists of peaks and valleys, reference specimens contain precisely machined in peaks and valleys in various shapes and amplitudes that are known, they're measured, and they're certified. Thus, the calibration process, well, basically taking the surface finish test specimen, measuring it with the surface finish gauge, ensures that the system is reading properly. So there's different style patches out there of different waveforms, but you will get a certification with them that defines what that calibration results are of that test specimen are. So it's important to verify that your surface gauge is using the same tip radius as the test patch was certified with. If you're trying to correct for or calibrate your probe, you want to be sure that the specimen was checked with the same type of stylize. Otherwise, you might be adjusting error into the system and put a little bias that wouldn't be right. Sometimes the thought is to have a specimen as close to the surface that you're measuring, but I think it might be better to use a specimen that uses a lot of the gauge's measuring range. Thus, you're more apt to have a more calibrated system, giving you more versatility throughout its whole measuring range. Another idea is to consider a double patch check, one for full range and then one for fine range. So this, helps to calibrate the system over its full range, but also can help to identify if the tip is wearing or becoming damaged over time. So again, something to consider for checking the performance of surface finish gauges. Now, traditionally, surface gauges is measured in a quality lab, back in the corner of the factory. But there are some shortcomings to this, older traditional method. It's reactive by nature. It helps prevent bad parts from being shipped, but it doesn't prevent bad parts from being manufactured. There's cost to this. The cost of moving the parts to a lab, producing bad parts while they're being manufactured. And so there's a lot of unneeded and wasted time in this process. And by the time you find something wrong, you might have made thousands of parts, and it's hard to determine where that process error is. And it's really a no-go method for inspection. The parts are qualified as good or bad, but it does nothing in the terms of preventing bad parts from being manufactured. There's lots of cost associated with that, and it only recognizes deviations so severe that makes the part good or bad. And of course, like I mentioned, there's that lag time between the part when the part was manufactured and when it was inspected. So there's really a productivity change going on now, where we're giving measuring tools to the machine tool operator to provide information for decision making right at the point of manufacture. So we're bringing portable surface finish testing equipment to the point of manufacture so that we can find bad parts immediately. There is no lag time between the manufacturer and the part inspection. It prevents bad parts from being manufactured because you can sense when something's getting close to being bad, and maybe you can allow for adjustment of the machine tool to prevent that part from being manufactured. So bringing portability of surface finish gauges right to the machine tool is a very big productivity change. So operators need tools that are simple to use. Most operators are experts at running their machines. They are most likely not experts on surface finish measurement. And, it's hard to keep updated on all these surface finish changes. Surface finish parameters change, there's new ones, there's new call-outs and prints and so forth. So, even a seasoned quality control professional can have a tough time grasping the intricacies of surface tech metrology. So it's important to have tools that are easy to use for the operator. And that's what Mahr offers. We offer a complete portfolio of portable surface finish gauges meant for the shop floor that are easy and simple to use. And the one that's been around for a while is the Mahr Pocket Surf, We're up to PocketSurf 4 now, and we think it's one of the easiest to use instruments out there. It's portable. It has limited selection done by switches. It's simple. It has a simple and easy to understand display. It can provide the three most common roughness parameters to the user, whether it be RA, R sub Z, or R max. We have data output with it. And what's unique about it, and most unique product like its type, is its 4-position probe. And of course, there's a large range of accessories, probes, and stands to be used with the PocketSurf. So, just a quick overview here. You have some buttons that allow us to set the parameters, a nice display, a simple one-button operation. The probe has these unique 4 probe positions, which increases the versatility. It can read in inches or micrometers. It has its data output, and it can be used vertically, horizontally, even upside down to give us good results. We've sold thousands of them over the years, and we're up to PocketSurf 4 now. We've been increasing its capabilities, its speeds of response, doing some small things to increase battery life and so forth, a newer, more powerful data output. But all those changes, it still uses the same one-button operation, the same probes, and it's just getting better with time. Typical applications are right on the machine for fast inspection or next to the machine for part verification. Typical applications can be with stands. We have tools for helping to measure crankshafts, small bore probes to get into small holes. And you can see there's a whole family of accessories available for the PocketSurf 4. Now, a number of years ago, we introduced the PS10, which is another skidded roughness system. And this was really unique to the line of portable surface finish gauges. The idea here was that we wanted to bring ease of use, but more capabilities to the machine tool operator. So what we tried to do was give us a nice large screen that really acted like a mobile phone. It has the ability to pull up menus, to slide the menus up and down, make selections with a touchscreen type of display. So the idea is that if an operator is used to using a smartphone, he's going to be able to pick up the PS10 and use this with great simplicity. And the large screen gives us a battery charge condition. We can set soft keys. It's touch screen. We have an integrated removable calibration standard built into the system. It has a removable drive system for more versatility, a probe protection device, a large green start button, which also acts as the home button within our menu system. And it has a battery indicator light that lets us know when the battery is getting time for a recharge. And as I mentioned, the drive is separable so that you can mount it into stands, put it on the parts that are within the machine tool. And you can see there's a nice large display that shows us our parameters. We have the ability to move this up and down, and makes it very simple to use. So we think that the PS10 is very simple to operate, just like a smartphone. Plus, it saves training time. You don't have to be a surface finish expert to use this product. The workpieces don't have to be aligned as critically as this, because with its portable drive system, you can put the drive sometimes right on the part. It's very fast to respond. It logs all the information right on the device in a PDF format. So if you plug the system into a PC, it acts like a stick where you can see the PDF files of your past measurement. a simple to use start button, which really saves time, and really you get a lot of value out of the product because generally it's a small investment, but you get some pretty accurate measuring results. So like I said, the PS10 acts as a memory stick, or you can add more memory if you want by adding a small SD memory stick within it. It has the calibration standard, so it's easy to ensure that the system is ready to go at any time. Here's an example of a PDF format with the drive that you can store the data to get your measured results along with the profile of the trays. Customers can also customize the header to put their own logos on there if needed. With the PS10, you can also connect it directly to our free Mahr software so that the data can be transferred and put into an Excel file for easy storage, classification. You can create your own forms, and you can choose to collect data automatically or start the function through the remote control capabilities of the PS10. Makes it a very powerful data collection system. Again, applications of measuring roughness right on the part, putting the drive into a little stand to help bring it to the part. Lots of flexibility with the PS10 in terms of stands and different ways of using it. Our latest addition is the M310, another skidded roughness system. This looks very much like the PS10, but it's been updated to have some more LED signals on it to help the user understand what's going on. We have a lot more interface capabilities with the M310 in terms of the USB socket for adding a micro SD card. We have the capabilities now of sending out information about the gauge with the data. Talk about that. And now we also have the capability of doing printing out of the information to a portable printer. Now you may think that, well, why do I need paper out on the shop floor? Well, paper is a great way of, especially at the point of manufacture, to help discuss and show people what's going on with the process. So at the point of manufacture, sometimes a small piece of paper can be worth 1,000 words in terms of what's going on in the surface. So this is a great addition to the portable surface finish line. Again, this has 31 parameters. It has the various amplitude density curve. Bearing curves can be shown on the device. The ability to select tolerances, your surface finish parameters. So it has lots of capabilities, and with the large screen, it's very simple to use. We have the USB Bluetooth printer docking station, which can do our curves for us. We can look at the capabilities of the device status clearly. It has a rechargeable battery for over 1,200 measurements without having to recharge the device. And it's really meant to be used on the shop floor in oily type environments, and that oils won't damage the plastic or the start button or the display on the product. It's really robust, meant to be used at the point of manufacture. Again, this has the remote drive unit, and they can be separated and be built into a different type of gauging applications, the integrated calibration standard, and it comes with a nice transport case as part of the package. What's really important is the interfacing on the 310. So Again, we can collect data through Marcom. We can increase the storage capabilities. It has the ability to, if you want, add a keyboard or a printer or a barcode scanner, so that now, like, a user, whenever a new part comes along to be measured, he could scan a barcode on the routing information, and that would load for him all the different parameters that need to be measured. So it can be pre-set up based on reading a barcode. And we also have the capability for a lot of remote control functions via ASCII commands. So if you want to build a surface finish device into a fixture gauge for helping the operator to align the part, or you want to put this into an automated process, the M310 has the interface capabilities to do that. Another important feature is that, one of the big things that's been missing with data collection is, we have the ability to collect the data, timestamp it, maybe know who the operator was. But one of the missing pieces of information was what gauge made the measurement. So with the M310, we can identify, the part number of the gauge, its specific serial number, and that can become part of the data collection process. So now we know what the gauge was, we know when it was calibrated, we have the data, we have the time, so it really puts together in one place all the information for a good data collection process. And like I said, we can control the M310 with ASCII commands, so it's a great way of building the system into an automated process, whether it be a manual measuring system or creating a custom solution where the operator simply puts the part onto a gauge, the probe is protected, and even when the part is sensed, we can begin making our measuring process. So we have lots of applications for in-process control with the M310. And then finally, Mahr has a skidless roughness and waviness profiling system that's portable, that can be used at the point of manufacture, and that's the M400. This is, again, a skidless roughness profiling system, very similar capabilities as the other systems, with a large display, simple to start using the green start button, so it's quite clear what's going on here. We use a unique breakaway probe design. Now you can imagine with a profiling system that the stylus has to be a pretty fine and delicate piece of equipment. But rather than having a stylus that is fixed to the probe, we use magnets to hold the stylus in place. So if it's subjected to a quick hit or something like that, the probe will just break away based on the magnets, and then you can put it back into place. And again, we also have another way of protecting the probe is we use a motorized positioning system that the operator simply has to place the stylus just above the part. And when he begins his start measuring cycle, the probe is going to come down and touch the part. It will automatically sense when the probe is in position and then begin the measuring cycle. So again, another way of protecting the part probe from damage. So with a skidless tracing system, with a very high precision probe, that offers a fast arm change due to the magnetic breakaway probe system. We can get our probe aligned very quickly. In fact, we don't have to align it. We just have to position it above the part, and then it'll take care of itself. It comes with all the international standards for measuring waviness and roughness and profile. And we can document this information through the integrated printer that's built into the system. And there are lots of different probe styli available for small holes, for grooves and so forth, for doing over radii and so forth. Lots of capabilities with the M400. And then again, because it's a skidless system, we can analyze the profile for its profile content, for the roughness, for its waviness conditions. All can be filtered out so that you can focus on what's the most important characteristic that you need to work with. Again, it's very, very portable at the point of manufacture system, whether it's bringing the part to the gauge or the gauge to the part, or fixturing it into a work stand and so forth. The M400 has a lot of system capabilities. So a pretty good line of portable shop floor surface finish measuring systems between the Pocket Surf 4 all the way up to the M400. What's important to note at this time also is that many of these products are in our current promotion of Mahr lights, and they're at promotional prices now through the end of June, offering the PS10 at a low price of $23.50. All the features that we talked about, it's smart-like phone operation. The M310 is available at promotional prices. This one, again, the same smartphone operation, capability of doing printouts and so forth, and the capability of being built into a automated surface finish operation. Again, this can be connected to our free Mahrcom software, which is available through download from the Mahr.com website. And even the M400 is available through the Mahr Lights promotion at a price, again, with all its features of doing roughness, waviness, and profiling at a skidless measuring system. So that's it. That's in review. Surface finish is we've learned that surface finish is an important parameter or feature to measure. Production automation calls for inspection at the point of manufacture. So we want to put into the user's gauging that is powerful but simple to operate. So I think with Mahr's complete line of MahrSurf mobile roughness instruments, we have the great solutions to do that and to make it easy to use for the machine operator. So thank you for your attention today. Hopefully, you learned a little bit about the surface finish parameters, what to look for, why it's important, why surface finish is an important feature. So again, thank you for attending. If you had any questions, make sure you put them into the chat feature, and I will respond to them as soon as I receive them. Thanks for your attention.